All right. As a physicist turned engineer and designer, Amitabh enjoys solving interdisciplinary problems in electronics, mechanics, and human-computer interaction with a focus on rapid prototyping and manufacturing. During this talk, Amitabh explains the working principle behind refrigeration systems, how to make one yourself. Please welcome to the Hackaday Supercon stage, Amitabh Shrivastava.
Thank you so much. Wow. It's crazy being on this side of the camera. Thank you all for coming. Before I begin, I wanted to introduce my collaborator, Aaron Cohen, as a third-generation HVAC refrigeration guy. Aaron has done custom HVAC solutions for 15 years, and then he has broken the cycle and turned into a mechanical engineering consultant. But he still feels strongly about the refrigeration industry and is looking to advance that. And that's what Refrigediro is. It's Aaron and my attempt to open source information about DIY refrigeration systems. So I should address the elephant in the room, the refrigerated backpack. So it's a complete compressor-based refrigeration system on a 20-pound backpack that chills down that bottle of Fireball down to -5 degrees Celsius. The white stuff right here, frost. So, I know what you're thinking. Why Fireball? Right. Well, it's two very good reasons. Number one, I couldn't give up the pun of a chilled Fireball. And number two, my girlfriend, who's right there, loves Fireball. So, two excellent reasons. Why a backpack, right? Why a refrigerated backpack? To give an answer to that, I'll have to take you back 2 months. 2 months back, I was looking for a water chiller for my laser cutter. And I looked at the options online, and they were either too expensive or not good enough. The expensive ones, $400 to $500. The cheap ones, $200, but they were radiative only. That means they were not able to cool the temperature below ambient. And all this while, I saw that on Amazon, I could just buy an ice maker for $90. So something didn't add up. Like, you have a refrigeration thingy, and that's $90. So I bought it. And in true Hackaday fashion, before turning it on, just started ripping it apart. I took apart all the sensors, the electronics, the casing. I didn't need any of that. All I needed was this refrigeration circuit. And it looks pretty simple because it is. It's some copper tubing, a radiator, and a compressor. I was like, oh, I wonder if I could make this into a water chiller, right? And at this point, all I know is the thing on top gets cold, the thing on the side gets hot. So very carefully, I started bending the copper tubing to get to this stage where the thing that gets cold is like bent down, and I put it in an ice box full of water, and I connected an aquarium thermostat to switch the condenser on and off for temperature control, and added a little aquarium pump. And for less than $150, I had something that was actually slightly better than the $500 water chiller. So I wrote an instructable about this, and it seems like people were interested. They were interested in not only using it for a laser cutter, but for controlling the temperature of their beer fermentation setups. I was interested in using it to water cool my mattress, because I'm a sweaty sleeper. So I could buy for $80 a mattress cover, which has silicone tubing all over, and I could just run cool water through it to get a water-cooled mattress for a fifth to a tenth the price of commercial setups, right? And this was also around the time that I was taking off the window AC units and sealing up the windows for the winter. And I was thinking, well, the refrigeration circuit really is quite simple. I wonder if I could add a reversing valve to the window AC unit so that it could also be a heat pump for the winter. And you might be thinking, yeah, I mean, technically that's true, but you'd have issues with condensation or frost formation on the radiator side, and how would you, interact with the AC electronics? And I agree with all of those points, and I'm like, those are the interesting challenges that open source hardware should be trying to solve. So at this point, I'm talking to anybody and everybody about refrigeration and the potential projects that could come out of it. And that's where I meet Aaron through a mutual friend, Owen. And Aaron agrees that the refrigeration industry is very closed off and like kind of stuck in the 60s. And in fact, it's so closed off that it's regular practice for warehouse suppliers to mark up their prices by 100%, double, for people who are not in the HVAC industry. In fact, as an HVAC technician, if you go and take a non-HVAC guy with you to a warehouse, that's really frowned upon. And all this around an industry where the core concept is really quite simple. So let me take you on a journey of the refrigeration cycle, right? A basic refrigeration cycle is this, and the system has two parts, a high pressure side on the right and a low pressure side on the left. So we start down at the compressor, right? It takes in low pressure vapor and compresses it into high pressure vapor. So when it does that, compressing all that gas increases its temperature as well. So the compressor outputs high pressure hot vapor that then gets pushed into a condenser. And a condenser is just something with a lot of surface area and air blowing over it, also called a radiator. And what happens is that the hot vapor cools down, and because the pressure is very high, it liquefies or condenses, hence the name condenser, right? So now you have high pressure liquid refrigerant that gets pushed through a dryer, which is only there to remove any moisture, because moisture can corrode and things like that. And then it gets pushed through this capillary tube or other expansion device, which just presents a lot of resistance to the flow. So this high pressure liquid is squeezing through this capillary tube, and at the end, it finds itself in a low pressure environment, and it just expands very rapidly. And when it does that, the rapid expansion creates a lot of surface area, and those intermolecular bonds that are kind of broken, that requires energy. So that energy is taken from the evaporator or anything that the evaporator is trying to cool, right? And then your low pressure vapor just gets back into the compressor. Simple as that. So let's see how this cycle plays out in our backpack right here. We have here a very cute little compressor. It's actually a brushless DC compressor that's driven by this module, which is similar to an O drive. Because it's a brushless DC compressor, it's much smaller in size than the conventional AC motor compressors, and also runs a little bit quieter. There's no sparks that it produces also, so it's relatively safe. So it's taking in low pressure vapor and then pushing it out through this tube, which is quite hot, and putting the high pressure vapor through this condenser unit. This condenser unit is called a microchannel condenser. That just means it has multiple channels along this track, and essentially a lot of surface area in a small volume. It's almost like a fractal structure. The fins that you see have fins themselves. So this small unit has more surface area than a typical window AC unit radiator. So after the hot vapor goes through that, it goes through this dryer unit, right? And now this relatively, it's pretty much at ambient temperature at this point. Liquid refrigerant goes down here and here into this coiled up capillary tube. As it expands out, right here is where you would first see frost forming when you switch on the unit. Because right here is the first time you're getting that expansion, and reduction in temperature. Underneath all this insulation is an ingenious device called a microplate heat exchanger. It has a lot of parallel plates of copper and stainless steel. And because there's a lot of plates, there's a lot of surface area in between them. Again, heat exchange is all about the surface area. The refrigerant flows through the copper plates, and through the stainless steel plates, I'm passing this fireball alcohol through a small peristaltic pump. And as the alcohol flows through, it exchanges energy with the refrigerant and cools down. We just have a little aquarium-style temperature controller here that's measuring the temperature of the alcohol, and right now we're at -6 degrees Celsius. So yeah, not too much. The whole thing consumes about 120 watts of power. I have a 300 watt-hour battery, so it lasts for 2 to 3 hours. All right, so now let's see how you would go about making a system like this for yourself, right? The first step is the most difficult, and where I think we need to do the most amount of work, is selecting the right components that you want to use. The condenser units, microplate, the compressor, they all come with several ratings about what refrigerant they can work with, what power levels. But I think that this is a system with too many variables and too many choices. I think we need to create hacker-friendly sets of things that just work together that you can have and kind of in a plug-and-play manner. All of these can be purchased on AliExpress for relatively cheap prices. So I think that just creating projects and kind of showing the methodology behind the selection of the components, that would take us a long way to creating DIY refrigerators. Once you've selected the components, you just place them in the positions that you want, and the next step is to bend some copper wires, copper tubing, to connect them all together. Copper tubing is relatively soft, and here you can see me just bending it by hand around a soda can. I think there's a lot of potential for interesting artwork to be done in kind of like a Mohit Bhaut-esque manner for refrigeration. Like, you see this frost forming right here. Imagine like a snowflake-style copper tube that forms its own frost. I think that we just haven't even thought about the things that could be possible if people started making their own condenser and evaporators. You'll want to make sure not to contaminate the inside of the tube with anything. Even moisture from the air will need to be vacuumed out later. So the cleaner you can make this setup, the better time you'll have. The next step is to braze the components together. Brazing is similar to soldering. It can connect dissimilar metals together. Using high silver brazing wire, you can connect copper to stainless steel, for example. You'll just want to make sure to use a wet paper towel to protect the components that are heat sensitive. And you can use an oxyacetylene torch for finer control, but you can get the same results from a propane torch as well. Next comes testing and making sure that the system is airtight. And you can do that by pressurizing the system with nitrogen or other inert gas and dunking it in water. And if you don't see bubbles, you're good to go. Or you can pull a vacuum and just wait for several hours and make sure that the pressure does not rise. The next step after that is just pulling a vacuum and start charging the system. So you start charging the system from the low pressure side, and it's traditional to use Shrivastava valves, which are same kind of valves that are used in bicycle tires. and the automotive connectors for those are relatively inexpensively available. Here, the yellow tube is connected to a can of propane, which is the refrigerant used. And you also see 2 pressure sensors and 2 temperature sensors. And all you're doing here is you're just making sure that the high pressure side is high enough pressure and the low pressure side is low enough pressure. And you're just looking some lookup tables based on the refrigerant that you're using. If you have too little refrigerant, then the high pressure side won't be high enough pressure. If you have too much refrigerant, then the low pressure side would be too high pressure, right? So this is something that I think can be easily automated with a $50 Arduino shield if we wanted to do that. And there you have it. It's a working refrigeration loop. And I think that the simplicity of it just betrays that there are so many possibilities with it. In fact, let me paint a picture of what a future could look like with weirder refrigeration systems. It's a hot summer morning. Before your alarm goes off, your house starts cooling down, except there are no air vents, no drafts. The refrigerant line running along the ceiling and walls cool down the house without necessarily moving air around. You wake up and head to the kitchen and open the fruits cabinet. You find fruit at the perfect temperature and humidity. You chuckle, thinking how not too far in the past, all the refrigerated food in the house used to be kept in the single cabinet, simply called refrigerator. How strange. Different foods need different temperatures. At this point, each cabinet of your kitchen is a separate temperature controlled environment. You head out into the patio, and as you sit down, the patio furniture reduces and chills down to a perfect temperature, even though it's in direct sunlight. Sure, it's a little annoying to move patio furniture around because the coolant lines get in the way. But that's a small price to pay for comfort. You head to your cold shower, you weirdo. But you're greeted with actually cold water, not the lukewarm water supplied by the city, because your house cooling supply cools down your water. You dry off with a perfectly warm towel. Some clever engineering uses the excess heat from your refrigeration system to keep your towels warm and at that perfect, just out of the dryer temperature. Time to head to work. Your ultra-thin laptop boots up immediately. And of course it does. It's a computing beast because it's plugged into the wall, not only for power, but also for coolant. Gone are the days where you used to move air around electronics to cool them. PlayStations, televisions, even power adapters last longer and run cooler because they are cooled by the house coolant supply. Turns out you have to refabricate a part. So you head into the workshop and switch on the CNC machine. While you wait for the CNC machine to do its job, you carve a wooden project with an orbital sander. The orbital sander you use is a fifth the size of a traditional orbital sander because it's a brushless DC motor, water-cooled system with coolant running along the hose of the vacuum as well. Because you're not moving all that air around, it doesn't move as much dust around as well, leading to a cleaner system. You barely hear the hum of the CNC machine as it's cutting through aluminum because it's a water-cooled spindle. It's smaller, lasts longer, and because it weighs less, the whole CNC machine is leaner and costs less. Time for lunch. You pick up your jacket off of the hook and put it on. As you do, you feel a chill from the phase change material in the jacket that maintains itself at a perfect temperature, much like melting ice. You take your electric scooter to the nearby cafe, and as you dock it, the scooter not only starts charging, the coolant supply cools the battery to charge faster and increase the battery life. You put your jacket on the complementary coolant hook, where the cafe cooling system recharges the jacket for a journey back out. That's the end to the story. Thank you. Thank you very much. So what's next? Hopefully I've convinced you that there is untapped potential in cooling systems. And I didn't even go into the possibilities for phase change materials, for refrigerators in cold supply chain for the developing world, for everything from vaccines to food preservation, or the insane levels of carbon emissions from the HVAC and refrigeration industry currently. And for good reason. I genuinely am not driven by those causes. Left to our own, Aaron and I will work on fun projects like a Cold Stone ice cream machine backpack, or a backpack snowblower, or heck, doing a trek in Death Valley on the hottest day of the year using a refrigerated suit. But if you feel strongly about something that could use open source refrigeration systems, come talk to us, because we'd love to help you out. Thank you.